Welcome. In this video, I am going to be discussing a problem that is dealing with concepts of both momentum and energy. What we have in our hands is a system of two blocks, as we can see, that are coming toward each other with separate velocities v1 and v2. The masses of blocks are also not the same, as indicated with the variables m1 and m2. One of the blocks, namely m2, contains or has attached a spring on it of stiffness K. So we're asked to find, when these two blocks actually collide, what is going to be the max compression of the attached spring on M2. So as always with any problem that we do in physics, we want to make a list again of givens and unknowns. In this case, I've already done it a priori, and this is what you are actually given in this problem. We're given, of course, the masses, the initial velocities, as well as the stiffness of the attached spring, and we're trying to find the maximum compression of that spring. So to begin right now, as with any problem, we're trying to see what topic we are in. What topic are we working in right now? So we're looking for trigger words. And in the description, we might see the word collide right now. That should be a trigger word for conservation of either momentum or angular momentum in the future. Now, in terms of energy, because I have this spring right now attached on M2, it means that the collision that is going to happen between the blocks is going to be smooth, and it's going to be of elastic nature, such that the energy is actually going to be conserved during this collision. So this leads me to have momentum conservation from the collide and energy conservation from the fact that we're, conserving energy through the spring during the collision. That is two conservation laws. And for any conservation law, what I need to have in place is two frames that I'm going to be comparing quantities. One of the frames here could very well be the right before, right? So right before these two masses touch each other, that could be the frame one that we start our comparison from. And then we let the collision, actually go on, and then we actually see frame two where the maximum compression is going to happen. And that's exactly what I've done over here, laying out the frames for you. So in frame one, we are just about to collide here with each mass. And again, we can see how they're coming together. And then in frame two, we have them collided in such a way that the spring has maximally compressed right here. So it begs the question right now, what is the velocity going to be right now for this frame two? Are these going to move at different velocities during maximum compression? Is it going to be the same velocity? And if so, what is the value of that velocity right now? So to understand, our initial thought here may be that the actual velocity that they move is the same and is actually zero. It makes sense. They're coming together. Why not have the spring maximally compressed when these two guys are literally stationary? But is that actually going to happen? Are we going to have them ever be stationary during the collision? And for that to be answered, we should consider some of the extreme cases that we could have in this problem. Let's say right now that I made M1 over here very big, and its velocity right here also very big as well. Very big. Both of these quantities extremely big, so tending to infinity if you must. Right now, M2, as it's coming in, it looks like this, basically. It looks like it's non-existent right now to M1. So when the collision happens, M1 right now doesn't even realize that M2 collided with it, and everybody here just proceeds to the right like nothing happened at all. So in this case, we can clearly see that the maximum compression will not happen when the two velocities are zero, because this will just continue going to the right here during the collision, even at maximum compression. So again, we can reverse the logic here, and we could, for example, make M1 here to be extremely small and also have its velocity be extremely small as well. and then make M2 be the massive one right now. And we can see that the exact reverse happens. When M2 collides with M1 right now, it doesn't even realize that M1 is there, and everybody just proceeds to the left over here, even during maximum compression. There's only one unique scenario where actually the maximum compression here is going to happen when the velocities of the two masses is 0. And that scenario is when they both are coming in with the same initial velocity, and they also happen to have right now the same mass. So in other words, when their momenta are equal sizes right now, and they collide, the maximum compression is going to happen when the actual velocity of these masses has gone down to 0. And this is the only case when this will happen. So take this with a grain of salt and understand that the maximum compression could happen when the velocities are 0, but more importantly, in general, it will happen when the velocities are exactly the same. So for that, let me do a quick demonstration of how it looks like visually, the entire collision, using my two hands right now. So over here right now, I'm going to have M1 and M2 with my thumb representing the spring right now. So they're coming together right now. And again, let's assume for the purpose of discussion that M1 is the guy that carries the bigger momentum right now. He is bigger in terms of P versus, M2. So he's going to be the driver of the motion during the collision over here. Now let's see again. As M1 and M2 are coming together right now, so the spring first encounters M1 right now, but M1 is not really phased by the spring. The spring starts getting compressed, and over here we have them both move to the right. Maximum compression happens here, and then the spring unfolds again, thrusting M2 forwards, and then M1 trailing behind it. So this is what happens again in the case that M1 is the more massive. One more time, so we actually get to see it in detail. Again, M1 and M2 come together right now. We have a collision starting when they touch right here. M1 is the driver right now, so let me start this collision from here. M1 is the driver, which means he's going to drive the system to the right. He wins the momentum war. The spring is compressing. Right now we're at maximum compression, and this moment we're actually moving at the same velocity, and then the spring opens up and thrusts M2 forwards as M1 trails behind because of that. So this is how the collision actually looks like. And the velocity that the two will move in common right now, we will actually call it something special. We'll call it VCOM, because that is secretly the center of mass velocity of the entire M1 plus M2 system. So if we were to find the center of mass of M1 and M2, we would see that it would move at velocity VCOM throughout this interaction. The VCOM will not change as momentum is conserved. More on that in a future discussion of the relationship between VCOM and momentum conservation. But for now, it suffices to know that in frame 2, we're going to be moving at the same velocity at maximum compression. Now, what direction is going to win over here? Not knowing the numbers means that the direction of the VCOM vector is ambivalent. We don't know where it's going to point. So we'll have to eventually take a guess. I'm going to go with my original, demonstration where I said that M1 wins the battle here. And I'm going to say that this ambivalent vector actually points to the right, like this. If I'm wrong, the only thing that is going to happen is at the very end, the VCOM here will have a negative actual value. But size-wise, it's going to be exactly the same, so it won't affect my math at all. Plus, in the energy considerations, VCOM gets squared, so the signage right now of VCOM is completely irrelevant because of the square factor. Anyhow, over here now, we want to see how we can measure the spring compression as well, like how you measure a spring compression on a moving object right now. The hint here is we can suppose that we do the measurement with respect to the moving mass that carries that spring. And how we do that right now, we can presume that the spring right now the equilibrium is right there for this spring. So this is x equals 0. And of course, right here is the position, the leftmost position of M2. How I'm going to use this to measure the actual compression, I'm going to copy this right now and preserve it. Could have done this using my hands right now on the diagram if I wanted to, but I'm not gonna, since I have one node, I might as well do exactly this right here. And then just pick those up and line them up, line up the solid line with M2 again over here, and you can see where the equilibrium would fall if our reference frame of measurement is M2, which means right now our spring actually finds itself right there. And the compression that we're looking for, that X max, is actually this quantity if you want to visualize it right now. So this is what we know, and this is what we're solving for. Now, to start us off, we need some information on the momenta. To count momentum, we need an axis because momentum is a vector and it actually needs a reference frame and an axis. Momentum right now is conserved with respect to the ground reference frame, as during the collision, the internal forces of M1 and M2 are actually vanishing. So momentum is conserved in the ground reference frame right now, which means, again, this is the reference frame where I'm going to be looking at the velocities that I put inside my momenta. And if I'm in the ground reference frame, I need an axis right now that will do justice to the velocities at hand and will make it easier for me to calculate momentum. I see that everything is happening along the x direction right now, so I might as well pick one of the directions along the x to be positive. I'll choose arbitrarily to have this one to be positive so that I align with my unknown over here. You could have done it differently, it doesn't really matter. So that's my plus x. And now for the first frame, what I gotta do is I actually gotta find the initial momentum along the x direction. So P1x is what I'm looking for right here. So looking at M1 right now, his velocity is aligned right now with my choice of positive. So M1 will have a positive momentum and the value of it will be M1 V1 simply. The opposite is true for M2, which has an opposite directed velocity to my choice of positive. So it will have momentum negative and worth M2 V2. For frame 2 right now, they're both moving at the same velocity toward the right. I've assumed that they're moving to the right, but I know that they move at the same velocity. So if I want to calculate P2x over here, the final total momentum in the x, I got to sum the two masses together since they're acting like a unit right now. And I'm going to multiply by VCOM. The whole thing being positive because VCOM, I assumed, is going to be along my plus x. So I have this lined up. And I know right now that if momentum is conserved, these two momenta are actually going to be exactly the same thing. So I line them up, and I have right now what seems to be M1 V1 minus M2 V2 is equal to M1 plus M2 VCOM. So I'll call that right now my equation number 1. I'll come back to this in a second to trim it a little bit for reasons that will become obvious in a minute. Now, for energy to be conserved, I would like to make use of the work energy theorem by stating out that W net will be the total change in kinetic energy plus the total change in gravitational potential and spring potential as well. Now notice that everything is happening along a flat surface, so that automatically means nobody's height is changing and gravitational potential is in fact remaining the same. And also for W net, we should recall that only non-conservative forces make it on W net if we write our work energy theorem in this version. So only non-conservative forces would go here, such as an applied force, friction, etc. So we don't have any of those here, which makes this term a very big 0. So for the rest of them, for the kinetic energy, I have two masses that are changing their velocity during the interaction, M1 and M2. So I'll need individual terms for these two masses. To do that, for M1, I will factor M1 over 2 and compare the final and initial velocities of m1 right now. Then for m2, I will factor outside m2 over 2 and compare m2's initial to final velocity right here. And once I have that down, I'm looking at my spring now, and to see how the spring's potential has changed, I will factor out the k over 2 and compare final to initial stiffness right now squared. So I have this lined up, and I can see that the 2's here will just simply cancel to that 0, so I can get rid of them right now. And I gotta fill in what these values are from my individual diagrams. So starting with the actual compression, I can see from my diagrams right now that in the beginning, my spring was laying at the x equals 0 mark, while at the end, my spring was laying at the x equals x max mark. So I'm going to fill that information for the compression right here. This is x max, and this is 0. For the velocities, I know from my diagram again that in the beginning in frame 1, the velocities initial for m1 and m2 were called v1 and v2 respectively. And that's exactly what I'm going to put here for them in this equation. Now, as for the final velocities of m1 and m2, we know they are common, and the value of them, we called it vcom. So that's what I'm going to replace these with. Okay, so now that I have this at hand, I can go ahead and actually write out what I have. I have m1, opening up both terms over here in this expression, I have m1 vcom squared minus m1 v1 squared plus m2 vcom squared minus m2 v2 squared. And then for the spring, I have plus kx max squared. Okay, it would be useful for me right now to factor the vcom terms. So I would go over here, and if I was to factor right now vcom squared, I see that I would get simply the masses summed together, and then the rest would be exactly the same. So I'd still have over here minus m1 v1 squared, minus m2 v2 squared, and then plus kx max squared. The next move I'm going to make here is probably move this stuff on the other side over here. So I'm going to have right now, if I isolate for kx max squared, I'm going to have right now, let's see, m1 v1 squared plus m2 v2 squared minus vcom squared m1 plus m2 being multiplied by. Okay, so now at this stage, I could go ahead and start isolating for x max. And to do that, I'd have to divide both sides here by 1 over k. So the 1 over k would right now be multiplying this term right here. So I'm putting him in the bracket. And then the square root would come next to surround the whole thing. So I would be done here, besides the fact that I don't know right now what vcom squared is. However, I'd like to point your attention to the entire term right here, vcom squared times m1 plus m2. If there was a quick way, in order for me to skip some steps here, of mimicking it right now, I'd like to mimic it from the momentum equation that I have up there. And then I can make a very quick substitution of equation 1 into 2 and be done with my work. So how can I do that right now? Let's take a look. So the only difference between this and this right now is the vcom being squared. I can't really multiply both sides by vcom since I want the left-hand side right now to be completely determined in terms of original variables. vcom is an unknown, so I wouldn't want to do that. That's circular logic that leads nowhere. A quick algebra trick, though, to do this properly would be to simply square both sides like this. If I go ahead and square both sides right now, I end up having m1 plus m2 all squared times vcom squared, so I'm getting closer, and then on the right-hand side, I would end up having m1 v1 minus m2 v2 all squared. Okay, so is this what I wanted? Not quite, I have only a single factor of m1 plus m2, while here I have a square. So maybe the next thing I want to do here is divide both sides by a factor of m1 plus m2, so that the power of this drops to 1, and I have in the denominator of the right-hand side 1 factor of m1 plus m2, and that now looks exactly like what we wanted over here. So that's exactly what I will use right now to minimize the amount of steps I need to do in the energy equation. So I'll take right now equation 1 as is right now, the result at least that's important here, and I'll plug it into equation 2. That's exactly what I'm doing over here. So basically this is going to go in place of the red box right now, and let's see what we are left with if we do this actual manipulation. So the red box over here vanishes, and we are replacing it with this term. And now you can see that my answer is completely determined in terms of original variables. All I have to do right now is plug and chug the numbers that they give me in the beginning, and I can get very easily the amount that the spring compresses maximally. So this is how we go about it. And again, I hope this gives you a little bit of insight as to how we can think when momentum is conserved, when energy is conserved, and use a little bit of intuition when it comes to problems that involve springs, and when we want to see, for example, when something special happens, like when a spring is maximally compressed. We got to think of extreme cases sometimes to figure out the in-between case that we have in our hands. So I hope that this problem has helped. And again, thank you for watching.